Okay, so let's finish off the last three sections here of chapter 7. So we've got an example here of photon interactions, history of a 5 MeV photon in water. So as an illustration of the ideas here in chapter 6, we're going to look at a 5 MeV photon that's going into a tank of water. The energy is approximately the average energy of a photon of a 15 MeV linear accelerator beam. Now, we'll get to that in a little bit later. Why do we say MV here and then 5 MeV over here? So we'll get to that. So we assume that the water is sufficiently deep and broad that the photon expends all of its energy in the water without passing through and out of the water tank. So as discussed in chapter 5, the average distance of a photon will travel in a medium before interacting is called the mean free path. We learned that the mean free path is this. So for a 5 MeV photon in water, this is the linear attenuation coefficient. The mean free path is therefore 1 over that, which is 33 cm. Our photon travels an average of 33 cm before interacting. Note that if this photon enters a patient, it might pass through with no interaction at all because, a lot of patients aren't quite that thick, or parts of their body might not necessarily be that thick. There are a number of possible ways in which the photon can, in principle, interact with the electrons and nuclei in the water. Photon interactions with electrons include coherent scattering, photoelectric effect, and Compton scattering. Interactions with nuclei include pair production and photonuclear reactions. 5 MeV photon has the necessary 102 MeV threshold to produce an electron-positron pair. The 5 MeV photon in water has an 8.5% chance of pair production, 91.5% chance of interacting via Compton scattering. The likelihood of a photoelectric or coherent interaction is essentially zero for that particular energy for water. So assuming that the first interaction is Compton scattering, the minimum possible energy transfer in a Compton interaction is essentially zero. The maximum is 4.8, which occurs when the photon is scattered at 180 degrees. It can't give up all of its energy in a single interaction and conserve momentum. So a 4.8 MeV electron will travel about 2.5 centimeters, which is roughly D max for a 15 MeV beam. The average energy transferred to an electron is 3.14 MeV, which leaves us with 1.86 MeV for the average scattered photon. Under these circumstances, the scattering angle of the photon is 34 degrees. High energy photons have a tendency to be scattered in a forward direction. The scattered electron emerges at a 17-degree angle. The electron will travel 1.5 cm, and on average will lose about 1% of its energy to bremsstrahlung lung emission. The scattered photon will travel a mean distance of about 19 centimeters before it scatters again. The probability that this photon will interact via pair production is now lower than before, and photoelectric effect remains negligible. Compton scattering transfers an average energy of 0.97 MeV to the scattered electron, leaving 0.89 MeV for the photon. Photon scatters at 45 degrees. The scattered photon will travel a mean distance of 13 before interacting again. This time, probability of pair production is zero because the photon energy is now below 1.02. Photoelectric interactions will not be of importance until the photon energy is below 100 keV. So we'll look at table 7.1, or if you look at it, it shows successive average Compton scattering events, listing the energy of the incident photon, the energy of the scattered photon, the angle of scatter, and the energy imparted into the recoil electron. So let's take a quick look at it. Interaction number one, got the incoming interaction or incoming energy. You've got the mean free path, you've got the outgoing scattering angle. And then for the second, you're seeing basically the difference between this and this, which is where this comes from. You're seeing the mean free path here, the outgoing energy, scattering angle, the recoil electron, so on and so forth as you go through the myriad of other reactions here. The values in the table are based on the assumption that the photon always travels the mean distance and the electron energy transfer to the electron is the average value, which obviously is not going to occur in every case. The photon will continue to scatter via Compton until its energy is low enough that it's appreciable probability of absorption by the photoelectric effect becomes the main mechanism for it to disappear. For water, the probability of a photoelectric interaction becomes 50% just below 30 keV. So we've stopped the table there at that value. A photon will be absorbed and the photoelectron of approximately 27 keV will emerge. And it will scatter about 25 times before it is absorbed in a photoelectric interaction. Each of these electrons set in motion by Compton scattering will produce a track of ionization. And there is a chance that each of these electrons will produce a delta ray or emit Bremsstrahlung radiation, both of which will carry energy away from the track. The initial 5 MeV photon has an 8% chance of producing an electron-positron pair. So considering the possibility that the initial reaction event is pair production. The kinetic energies of the electron and positron will be on average the 1.02 MeV is the electron necessary to create the pair. The positron will annihilate with another electron in the water, and the 2511 keV annihilation photons will be produced traveling in opposite directions. The subsequent fate of these two photons can be followed by consulting table 7.1 at step 4, where you have about that energy. Now, Monte Carlo calculations. The interaction of radiation with matter is complex. The best way to calculate this is to simulate the interactions by following individual particles as they interact. It's pretty laborious. You need a computer. Many of the programs that were developed at national laboratories as part of high energy physics or nuclear weapons research. So one of the goals of radiation therapy physics is to compute the energy deposition of radiation and matter. Monte Carlo method is the gold standard for evaluating the detailed consequences of the interaction of radiation and matter. And it's one of the most accurate methods of accomplishing this if implemented properly. The incident radiation can be photons, electrons, neutrons, or protons, and we'll be primarily concerned with photons here. And Monte Carlo calculations use the basic physics of radiation interactions that we talked about in Chapter 6. Incident particles are sent in one at a time, and detailed history is followed, and that's called particle history. The direction of motion and the fluence spectrum of the incident particles must be known, as well as the geometry and composition of the patient. Computers got to keep track of the primary and all of the particles created by or set in motion by the incident particle. The secondary particles must also be followed, and they in turn may create or set in motion additional particles. So at every step, there is a range of possible interactions that can occur. These occur with probabilities that can be calculated from fundamental physics. These probabilities depend on the type of particle, energy, medium in which it finds itself. The properties of the medium, density, and composition may vary from place to place. At each step, the list of all particles must be kept in memory, along with their energies and directions of motion. The particles are followed, and then the energy deposition is recorded until they've lost all but an insignificant amount of their original energy. Large number of histories, perhaps millions to hundreds of millions, must be calculated before a meaningful average emerges, like this. Even after computation of large number of histories, there will remain some statistical uncertainty in the computed dose. An accuracy of 2% to the dose prescription point has been a clinical standard. So in the discussion of the 5 MeV photon water, they've chose average values at every step. In a Monte Carlo calculation, all possible events must be taken into account, although each possibility must be constrained by the probability of that event. So, for example, when the 5 MeV photon first interacts with water, there's an 8.5% chance that the interaction will be pair production and 91.5% chance it'll be Compton scattering. So you need a roulette wheel in which the ball will turn up in a bin labeled Compton scattering 91.5% of the time and pair production 8.5% of the time. Monte Carlo programs are written to simulate this. The name Monte Carlo is taken from the city of Monaco, which is famous for gambling. These computations are very intensive. These calculations require large amounts of computer time. For this reason, they've only recently begun to use for routine patient dose calculations. Commercially available software packages that are used to calculate the dose distributions are called treatment planning systems. Most of these do not use Monte Carlo dose calculation algorithms. The algorithms that are used are much faster and are reasonably accurate. The current dose calculation algorithms are not highly accurate, however, in or near inhomogeneities, particularly at boundaries because of the lack of CPE. Some significant discrepancies between the dose calculated by Monte Carlo techniques and simpler methods have been pointed out in the literature. There are a number of Monte Carlo software packages and are used in research calculations and radiation therapy. You can see them listed there. Commercial treatment planning systems are just beginning to incorporate these algorithms in their software. As computer hardware becomes faster, Monte Carlo dose calculations may become the clinical standard. So we'll see how that develops. So microscopic biological damage. A detailed discussion of the biological effect of radiation on cells is subject for another time. And there are some books here that they would refer to. High energy charged particles produce ionization of the atoms in the material through which they pass. It's in the form of tracks to the medium. The charged particles can be primary radiation, as for an electron or proton, or secondary electron charged particles set in motion by photons or neutrons. Most of the energy absorbed by ionizing radiation is ultimately converted into heat, which doesn't really change a lot. Some of it causes molecular bonds to be broken, which can result in biological damage. Biological damage to cells is thought to be caused principally by damage to DNA. If it's severe, it may interfere with normal cellular function, in particular, the ability to reproduce normally. There are two broad mechanisms by which this damage can occur. It can directly break molecular bonds in the DNA helix, and that's called a direct mechanism. The direct mechanism is of particular importance for high linear energy transfer radiation, such as produced by neutrons or alpha particles. The indirect mechanism of radiation is caused by reactive chemical species formed by the interaction of radiation with water. Cells are 70 to 80% water. The radiation products formed in water can attack DNA molecules, causing molecular bonds to break. In particular, free radicals formed as a result of the ionization of water are especially damaging. Free radicals are neutral atoms or molecules that have an unpaired electron and are highly reactive. Most of the damage is done by hydroxyl radical, which is denoted as this. Free radicals can diffuse far enough through the intracellular medium to reach DNA molecules. Both the indirect and the direct mechanisms operate simultaneously. The indirect is of particular importance for low LET. These tracks from this type of radiation are not as dense and therefore not as likely to cause direct damage to the DNA. Absorbed dose by itself does not tell the whole story with respect to biological damage. Biological damage depends on the LET of the radiation. High LET radiation can be more damaging per unit dose than low LET radiation. And there are more sections on this. And that leads us to the summary.